Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, should we start just 5 minutes late, or should we 10 minutes? Okay, so it's my pleasure to introduce today Rada Mihalcea, who is currently a faculty member at University of North Texas. She has done an extensive amount of research on word-sense disambiguation, question answering, parallel corpora, semantic parsing, unsupervised and weakly supervised methods in machine learning, to mention, I guess, just a few of the areas. She's highly active in the academic world, so probably you already know her, many of you. And she organized quite a few HLT and ACL workshops in the past few years. So we're happy to have her here to tell us about some of her latest work on text summarization and with graph-based ranking algorithms.
Well, I'm happy to be here. So I would like to start by thanking you for inviting me here. It's really a great pleasure to have the chance to be visiting with your group. And in particular, I would like to thank Silvio for taking care of all the details, for arranging my visit here. And what I would like to talk about today is a fairly recent research project that we started in our group for the application of graph-based ranking to text processing. And while I will emphasize the application to text summarization through sentence extraction, I will also outline a couple of other applications like word-sense ambiguation and keyphrase extraction. And to start with, I would like to try to give an idea of what's all this about using an analogy with what I believe it's a famous story. There was once upon a time a farm with animals, and all the animals were equal. And they were connected with some friendship relations, so some of them know some of the others. And as time was passing by, they got to be more and more connected. And anyways, the rule that was governing this farm was that all animals are equal. Now it happens that as time was passing by, some of the folks in the farm realized that they eventually were more special because they knew more of the other animals in the farm, so they started feeling a bit more important. Now, in turn, the other fellows who are now connected to these increasingly more important guys, they themselves started feeling more important and started to grow. And this was happening, and so the situation changed. And eventually, they also had to change the rule. So the rule that was governing the farm, all animals are equal, had to be updated, and it turned into all animals are equal, but some are more equal than others. And this is a quote from a famous story, George Orwell, Animals Farm. And while what I will be talking about today, it's somehow different, the essence is still there. So it's basically what's happening in a kind of social network, the kind of importance that you can establish for elements in the network in an iterative way. So here's what I'd like to talk about. First of all, just to try to give you an idea of what's going on in natural language processing at North Texas, people that are involved in the LIT lab, and what are some of the projects that we are currently working on. And then the bulk of the talk will be on the application of graph-based ranking to text processing. First of all, I'd like to show how this works and the kind of algorithm that we looked at so far. And then show the application to text summarization. It's really extractive summarization, so it's text summarization through sentence extraction. And then also outline the other application, unsupervised word-sense ambiguation and keyphrase extraction. So the Language and Information Technologies Lab at North Texas is a fairly young NLP group. It started in 2002 when I joined the University of North Texas. And the main areas of research are natural language processing and applied machine learning and information retrieval. There are 4 faculty from computer science and information sciences. We also have some faculty from the linguistics department, and then there are several students. It's really a growing group, so for now we have about 9 students, but there are more to join. Now, in terms of projects, one of the main projects has to do with devising tools for the resolution of semantic ambiguity of all words in open text. And basically what we try to do here is to come out with an algorithm that could find the meaning of all the words in a text using as little data as possible. And this is really an outside constraint. I mean, there is so little annotated data, semantically annotated data, so we have to limit ourselves to what's available. And in this particular work, we use SemCore, which is, in terms of annotation effort, seems pretty big. It's about 200 or 300,000 words. But then when you really try to derive some statistics out of it, it turns out that it's a fairly small corpus. So what we try to do is to exploit syntactic dependencies, so word dependencies that you can extract from a corpus, and then also information that you can get from a semantic network. And the main idea that we are applying here is to infer from specific to general, which is really the other way that you do it traditionally. And the main reason, again, is to try to get as much as we can from the little annotated data that is available out there. So, for instance, if we have a pair, drink water, which happen to occur in the corpus that we are training on, then we would leave that one level using the semantic network and make this to a more general, leave this to a more general level and infer consume liquid, and again with the corresponding senses. And once we have that, then we can go back and infer a more specific relation, for instance, take tip. So by doing this process, we actually have annotated data. We have some knowledge about take and t when they occur in this particular dependency, although it may happen that take and t did not even occur in the training corpus. So shortly, the way it works, we have we parse the entire SemCore and generate all the word pairs and also their generalization. So we'll go all the way up to the top level in the WordNet hierarchy. And then when we have to annotate a new text, again, we do again a syntactic parsing and find all the word pairs and their dependencies, and then try to find the most specific subsumer that appeared in the training data. If we happen to find an exact match, we are happy, and that's it, we have the senses. If not, then we will look again for a more general pair of concepts. And this approach, coupled with another approach with applies the semantic learning model, provided pretty good results in the recent Senseval 3 English all words task, which is a task that the goal of the task is to find the meaning of all words in open text. Another related project, or at least a project that we wanted to be related, is semantic parsing of open text. And I'm saying that we want it to be related because pretty much the people working in semantic parsing do not necessarily look at semantic classes, and the other way. People doing work in ambiguation do not necessarily look at semantic relation that you can eventually derive by doing semantic parsing. And our goal with these two different projects is to try at some point to put them together and combine semantic parsing and semantic disambiguation of word classes. So what we have here is a rule-based approach to semantic parsing, which is really a bit going against the mainstream. Pretty much everyone these days would apply statistical approaches to semantic parsing. So you have the FrameNet data or ProBack data and try to do some learning and with statistical approaches annotate new text. What we do instead, we try to learn some rules from FrameNet and also from WordNet to parse semantically open text. And the reason for doing this instead of applying a statistical approach is something that was mentioned by the FrameNet makers, Fillmore and Baker, that the data is not meant to be statistically significant, but rather representative for various language constructs. And so we believe that a rule-based approach would be more appropriate. And here is an example of rule learned from FrameNet. So if you have such an example occurring in the FrameNet corpus, I give him coffee. Then we extract various features and combine them into a rule that would tell us something about the roles and also about the position, voice, the syntactic role, and so forth. And then also we extract some rules from WordNet, like for nouns we would get the part of speech countability, whether it's singular or plural. More interestingly, for adjectives and adverbs, we also get the attribute. So for instance, for slow, we will derive from the relations encoded in WordNet. It is an attribute for speed. So if you encounter in a text slow car, you will know that that slow actually tells you something about the speed of the car, the degree, type, and so forth. And then we have again very shortly, a scoring matching algorithm that attempts to identify the best matching rule in the set of rules that we learned from FrameNet. And in this way, annotate new text. And currently, we are working to integrate selectional restrictions. So for instance, if you have these examples, which are really classic examples used in NLP classes, I eat spaghetti with marinara, or eat spaghetti with a fork, or eat spaghetti with pleasure, at least with the current state of FrameNet, there is no distinction between these examples. So all these would be annotated, most likely the prepositional phrase would be annotated as an instrument, because there is no connection between semantic relations and semantic classes. So that's something that we are trying to do currently in this line of work, to integrate FrameNet and VerbNet, which has a bit of selectional restrictions in there, and also WordNet, and try to solve this kind of examples that you can encounter in text.
Question. So for doing this kind of work, is there the equivalent of like the Pen-tree bank for semantic parsing, or is there a test set out there for this, or how do you do this?
Yes, there is. Well, FrameNet has examples from tree bank, so they just extracted sample sentences, and then ProBank apparently has annotated the entire Pen-tree bank with semantic roles, but there are different semantic roles. And this is a sample output. We are planning to put out there a demo in a few weeks. The kind of output that you get for a sample sentence. So it really looks like a syntactic tree, but it has semantic roles and other semantic annotations in there. So again, we had a demo at NACL earlier this year, and we plan on making this available on the web. Another project has to do with building annotated corpora, and we are trying to to rely really on volunteer contributions over the web. And this project is called Teach Computers. It's joint work with Tim Chlovsky. And in this project, we built so far data that was used in several sense-eval tree tasks. So we built annotated data annotated with word senses for English, for Romanian, also for a multilingual task. There are also other projects. Tim would have a collection of common sense assertions. There is also multilingual parallel text and several that are underway. And I'm taking this as a chance to make a bit of advertisement for an upcoming spring symposium that will organize exactly on this theme, knowledge collection from volunteer contributions. So if you are interested in this aspect, we'd love to see you there. And finally, TextRank, which has to do with the application of graph-based ranking algorithms to text processing. I won't say much at this point, since this is really the main focus of the talk, so I will come back with details in a little bit. And there are several other projects, word alignment with a focus on languages with scarce resources, chatting agents, storytelling and understanding, cross-language IR, question answering, and classification, and so forth. So there are several other larger or smaller projects that we currently work on. So graph-based ranking. These kind of algorithms have been traditionally and successfully used in a number of applications. In web link analysis, there are these famous examples, Clamber's hits, and then Brin PageRank, which turned out to be quite successful in doing search engine technologies. Also citation analysis, social networks, so these are kind of traditional applications for graph-based ranking algorithms. And just shortly the way it works, probably most of you or all of you are familiar with how this works, but only a very quick example. Basically, you start with the graph, and the original definition of these algorithms refers to directed graphs. So they are directed edges that connect the vertices. And you would initialize each vertex with a random value. It doesn't really matter with what value you start. And the idea in this algorithm is to determine the importance or the power of a vertex in the graph as a function of the importance of neighboring vertices. So for instance, here, I would determine the importance of vertex F as a function of vertices A, D, and E. So I would recompute the score of this vertex using a formula that relates all these neighboring vertices. Now, in turn, when I'm looking at another vertex, when I will consider the value of vertex F, I will take into account the new value. And this eventually iterates until at some point it's converging to a stable set of values. And the final values that you have are reflecting the importance of the vertices in the graph. Now, one interesting thing to notice about this is that although you may have identical local structure, like these two vertices D and F would have the same number of incoming links, same number of outgoing links, they still may end up with a completely different score and eventually a different position in the final ranking. And this is because these kind of algorithms would take into account global information that is drawn from the entire graph rather than relying only on local information. So the main idea is to decide the importance of a vertex within a graph by using a voting procedure. So when a vertex A links to a vertex B, basically it means that that vertex A votes for the vertex B. And through iterative voting, you end up with a ranking over all the vertices. And formally, here are some formulas that are used, some graph-based ranking algorithms. So one is HIT that I mentioned earlier, standing for Hyperlink-Induced Topic Search, proposed by Klemberg in 1999. It makes a distinction between authorities and hubs. So basically, for each vertex, you'll end up with two different scores, one indicating the authority score of the vertex and the other the hub score. Then there is PageRank, which combines incoming and outgoing links into one single formula. But again, the idea is the same, that you get the importance of a vertex as a function of neighboring vertices. So you look at all incoming links. And then there is positional function, which wasn't really, as far as I know, wasn't used a lot in any web link analysis or social networks. It's rather coming from the graph theory side. And again, it's producing two different scores for each vertex, one illustrating the positional power of a vertex and the other the positional weakness of that vertex. And in terms of convergence, basically an algorithm would converge when the error rate falls below a certain threshold. Now, this error rate would be computed as the difference between the current score of a vertex and the real score of the vertex. Now, since we don't know the real score of the vertex, this is approximated with...
Isn't it true that these are just systems of equations? So it seemed like the HITS algorithm, at least, was just a linear system. So you don't necessarily need an iterative algorithm to solve that.
You could do it. I mean, even PageRank, you would get the eigenvector for the largest eigenvalue. But to me, this is much more intuitive. And yes, there is an alternative way to do it. Yeah. So again, for convergence, you would usually have 20-40 iterations. It very much depends on the number of vertices or the number of how connected the graph is. But on average, for the kind of applications that we are looking at, you get 20-40 iterations. And you would have more iterations for undirected graphs. This is a change that we made in the original definition of the algorithm. So sometimes when you apply this to text processing, you cannot really establish a natural flow in the text. So it makes more sense to use an undirected graph. And the only issue that we had there was whether it still converges or not. And it does, but just usually it takes longer. So you would have a larger number of iterations. And here are the convergence curves. So you would have the number of iteration and error rates. You see the blue curve would show the convergence for a directed graph. It's a random graph with 250 vertices. And the red curve would show the convergence curve for the same graph, but with undirected edges. So it's more gradual.
Isn't that directed graph just a special case of directed graph if instead of each edge you use two edges for both directions?
Yes, it would be. Yes. Okay. So the flow can travel both ways.
Then you said that undirected graph takes more steps to iterate, to converge. So if you replace it with directed graph, won't it take less time to converge?
Yes, yes. That's what I was saying, that it takes longer, so you have more iterations. And also the final set of
yeah. Okay.
And the final set of values is also different. So if you look at directed or undirected graphs, you would get also a different set of scores and a different ranking. So what we are trying to do is to apply this kind of algorithms to text processing, and this would be suitable for those tasks where you need a ranking over cognitive units. And here by cognitive unit, I really mean anything that could be usually represented as text. It could be word senses, it could be words, it could be sentences, it could be documents, so pretty much any textual unit. And the main steps that one would follow, of course, would need to model the text as a graph if we want to apply a graph-based algorithm. Then run the algorithm to convergence and use the scores for application-specific decisions. So again, it depends on the kind of task that you are trying to solve, what are you going to use the scores for, the final score that you get from the ranking algorithm. So to model, first of all, to model the text as a graph, so we need to come out with representation where we have some vertices. So again, as I mentioned earlier, vertices could be pretty much anything. You could use words as vertices in a graph, or word senses, or sentences, or entire documents. And then to draw the edges between these vertices, you would use some relation between cognitive units, which again could be pretty much anything, depending on the application that you try to solve. It could be semantic relations, it could be a coherence relation, it could be similarity, and probably many others. So if we look at sentences and the similarity between sentences, or similarity between strings, then we have a solution for a sentence extraction task. So basically we end up with a ranking over sentences. If we look at word senses that, which are connected by semantic relations, then we end up with a solution for word ambiguation, where we get a ranking over possible senses for a word. So with the one that is comes out higher in the ranking would be eventually the more appropriate word sense. Then if we look at words and eventually co-occurrence relation, then we have a solution for keyword extraction, because we end up with scores attached to words, and those that have a higher score would be the words that have more importance for that particular text. So once we have this graph representation for the text, we would apply the graph-based ranking algorithm. Now there are a few extensions that we made to these algorithms. One is the one that I already mentioned, undirected graphs. So rather than using only directed graphs as they are in the original definition of the algorithms, we also look at convergence rates and behavior on undirected graphs. And this is because sometimes you cannot really get a natural flow in the text. So you cannot really say, well, the direction should be from this vertex to this other vertex. Like when you consider semantic relations, if you consider, say, part of relation, should it go from the part to the larger entity, or should it go, the direction, should it be the other way? So sometimes it's not clear how to set this direction. So in that case, we'll just go with an undirected graph. Then we also adapted this to a weighted graph. So in the traditional application of ranking algorithms, you usually have binary links. So either there is a link, like for instance, when you consider the web link analysis, you would either have a link between two pages or you wouldn't. Now in text processing, it's sometimes useful to also indicate the strength of the relation between entities. Like when you look at sentences, it may be useful to say not only that they share some concepts, but also what is the degree of similarity between these sentences. So we also adapted this to weighted graphs, and this resulted in some adapted formula for all the algorithms that we currently look at. So they would integrate the weight on the edges. Another extension, which really just fits well in this a framework we are currently experimenting with, and so I don't really have any results that would show the application of this extension to text processing. It's something that is actually inspired from Matt's work on topic-sensitive PageRank. So if you want to integrate some vertex-specific information, then rather than using some initial score for the vertices, which really will get lost as the algorithm iterates. So if you try to initialize the vertices with different values that would reflect some vertex-specific information, you are going to lose that with the algorithm. But instead, we would add this information by making a change in the formula. So we would add, for instance, for PageRank, you would add a weight in the first factor that will stay there and will reflect the initial information that you want to place on that vertex. So in this way, you could eventually integrate prior knowledge. Say if we are talking about word senses, it may be useful to try to integrate the frequency of that sense in some annotated corpora if that's available. Or you could integrate other vertex-specific features. Say, for instance, if you want to integrate the position of the text unit in the text. Like for sentence extraction, it may be useful to integrate the position of the sentence. Say, is the first sentence or is the last one. And that, again, would be something that is specific to a vertex and would be useful to be integrated. Again, I don't have any results reflected in this extension. It's something that we are currently working on. But it's a change that was made for the purpose of adapting this to text processing. And finally, once we have the ranking, we would use the scores for application-specific decisions. If we have a ranking over sentences, this gives us a sentence extraction tool. If we have ranking over words, it would be keyphrase extraction, ranking over word senses, and so forth. So I would like to focus more on the application to sentence extraction, but I will also outline the other two applications, word navigation and keyphrase extraction. So here, what happens is, first we build a graph. So we'll have all the sentences in the text added as vertices. And then a similarity between sentences will form the weighted edges. And then we run the graph-based ranking algorithm. We'll look at all those algorithms that I mentioned earlier, PageRank, hits, positional power, and weakness. And we'll keep the top and ranked sentences, which will make it to the final summary. And the basic idea is a process of recommendation. So when you have a sentence that addresses certain concepts, it's basically giving the reader a recommendation to look at other sentences that address similar concepts. So it's basically, say if there is a sentence that talks about Hurricane Gilbert, it will tell the reader, go and read these other sentences. They will tell you more about Hurricane Gilbert. So it's a process of recommendation that will eventually go in an iterative way. And so the most highly recommended sentences will make it higher in the ranking. And also, the recommendation coming from most influential sentences would have more importance in this iterative voting. And this relies on earlier ideas by Jerry Hobbs, who introduced this concept of text knitting. He suggested that a repetition in text is actually useful and something that you want to exploit, and it's something that knits the discourse together, and also relates to theories of text cohesion proposed by Halliday and Hassan in '79. So here is an example. It's a text from the Document Understanding Conference on Hurricane Gilbert. So there are 24 sentences, and starting with this text, this is the kind of graph that you obtain. So we have all the sentences added in the graph, and we have weighted edges. I'm only showing weights for edges that are incident on vertex 9, just because otherwise it would be there'll be too many numbers. But you get weights for all the edges.
A weight is a similarity between two sentences?
Yes. And then you run the graph-based ranking algorithm and end up with some scores which are indicated between brackets next to each vertex. And again, notice the thing that I was mentioning earlier. You may end up with different scores as you would if you would look at only local configuration. So for instance, these two vertices, 15 and 14, so the two sentences. Sentence 14 is connected to a larger number of other sentences in the text. So it would have a degree of 8 or 9. Whereas sentence 15 has a smaller degree. And still, sentence 15 is the one that is picked by this algorithm. And again, it's because it is based on global information.
So you must have some threshold on the similarity, because there's a connection with every sentence and every sentence. Every sentence and every other sentence, it just has a lower or higher similarity score. Right?
Yes, it depends. It depends on the kind of similarity that you use. You could use, for instance, something that uses TF-IDF scores, and so although two sentences would share prepositions, they wouldn't be considered to be similar. So it depends on what kind of similarity you use. At this point, with the kind of similarity that we use, and I'm going to show that in a minute, we are not really using any thresholds. So if there is a similarity from the point of view of that formula, then it's just put in there.
I'm focusing intuition on something. So how does this compare to just doing the centroid? There's something iterative about this, I think, but I don't see. So you can just find the centroid sentence. How is that different from doing what you're doing?
Well, the centroid would be basically finding, correct me if I'm wrong, you find the words that have the highest weight in the text, right? And then you compare the similarity of each sentence to that centroid.
I thought it was, I'm not sure how to be doing something. I thought it's the sentence that's most, on average, most similar to all other sentences.
I think you'd end up with about the same result when you know this. I don't think that would be any different.
So there is work, for instance, that would go step by step, would find the most important sentence, and then iteratively add one at a time, and you always compute the similarity with those sentences that are previously there, previously selected. This is really, it's iterative because it will not focus on one sentence. So the first selection that you make, like you find the most important sentence, is not necessarily going to stay there. So things can change. Things can change in time.
But do they change as you're picking one sentence? Do you recompute the graph? So given that you've picked one sentence.
No.
So the graph is static.
Yes, the graph, it's static, and it will iterate, and you end up with the ranking, and you just pick the top end. So there is no dynamic effect there that you pick one and then you readjust the graph. And this is the summary that was produced and the reference summaries. I don't want you to read those, but it's pretty similar information that is included in the automatic summary and the reference summaries. So in terms of sentence similarity, there is a number of similarity measures that one could think of. There were some that were suggested to us, like cosine, string kernels, and so forth. What we are currently using is a very simple measure that counts the number of common concepts, so we look only at open class words, and then divide that by the length of each sentence. And this is done because we don't want to favor longer sentences, and this is a measure that we get between every two sentences that would give us a sense of the similarity of those two sentences. Now, in terms of graph structure, we could use an undirected graph, and in this case, every sentence can recommend any other sentence. So if there is a connection between the two, there is a recommendation between those sentences. Now, we could also use, and we experimented with directed forward, in which case the recommendation only goes towards sentences that follow in the text. So this seems more appropriate for movie reviews or stories where the essence or the important part of the text would be more toward the end of the text. And directed backward, where the recommendation only goes towards sentences that precede in the text. And in this case, this kind of graph structure seems more appropriate for news article, where you have the essence somewhere at the beginning. So for the evaluation, we are doing a task-based evaluation. We use data from the document understanding conferences for single document summarization and multiple document summarization. For single doc summarization, the task was to produce a 100-word summary given a text. And then for multi-doc summarization, again, produce a 100-word summary, but looking at the cluster of documents. And on average, there are about 10 documents per cluster. And we are using data from 2002. The reason for using data from 2002 and not more recent data is because they decided to stop the single doc summarization, and we still wanted to see how this would work on producing single document summaries. But 2002 was the last year when there was such a task. So this year they have multi-doc summarization and other tasks. So in 2002 there were 567 single documents and 59 clusters. So one participant was supposed to produce summaries for 567 documents and then produce 59 multi-doc summaries. And the evaluation, we are doing it.
Sorry, is this the extracted summaries that you're using, or the human-generated summaries?
For evaluation, I'm using the human-generated summaries, although they are also extractive summaries,
Okay.
so they are both.
Because in 2002 they had both.
Yes. So I'm using an automatic evaluation with Rouge, which is n-gram-based evaluation. Probably you're all familiar with that. Is the alternative for blur from machine translation. And unigrams were found to have the highest correlation with human judgment. So that's what we are using also in these evaluations. And no stop word and setting. So this is the setting used for Rouge. And here are the results for single doc summarization. So we experimented with the 3 different graph structures that I mentioned: undirected, directed backward, and directed forward. And the 3 kinds of algorithm with hits, positional power and weakness, and page rank. And I'm also showing here for illustration and for comparison the top 5 systems in that evaluation. And the baseline. So the baseline is computed as the first sentences in a document. Now all these systems are evaluated again with Rouge for consistency purposes, although back in 2002 they were still doing human evaluation. So I re-evaluated all the systems, so I have the same scale. And see that the graph-based ranking algorithms do produce competitive results, although it is an unsupervised method. So some of the systems that made it in the top of the ranking were supervised, that were relying on data that was annotated by humans. So it depends on the amount of data that you have. While graph-based ranking, at least the method that we are working on in this particular experiment, is completely unsupervised. So you only look at the text to try to identify those sentences that are more important for the understanding of that text. And we also evaluated.
Did you happen to look and see how those scores changed as you iterated through your graph? Because like you could, like the first iteration would sort of tell you what Eric was asking, like if you just did sort of a single step of which sentences are most similar to the other sentences, and then, and then you could see like if it continues to improve after that, then you know that the graph algorithm is helping you out. Did you happen to look at that?
What I did, I compare with something that would not iterate at all. So you count only the degree of a vertex. So it's something that is static.
But did you look at the weight on those degree? I mean.
Yes. Okay. So if you would consider only local information, then the iterative algorithm beats that simpler algorithm. So, and actually that kind of algorithm was also suggested by Salton a year ago, when you would build a graph for a text and look at the degree of a node, and that would give you an idea of the importance of a sentence in the text. And when you do it in this way, you get better results. I mean, it's better with, and you have to take this with a grain of salt. I mean, in general, for text summarization, the baseline is already very high. So you get a bit higher with the algorithm that will look at the degree of a vertex, and somehow higher with the graph-based ranking algorithm. But the differences are really not that big. I mean, you cannot say it's a major improvement. It is somehow larger for multi-doc summarization. So what we did here, we actually do meta summarization. So we build summaries for the each document in the cluster, and then do a summary of this, a summary of summaries. And one of the main reasons for doing this is efficiency. It turned out to be significantly faster to do summaries for each document and then do a summary of all the of all the summaries in the cluster, rather than putting all the documents together and try to build one summary for all at once. And the task again is to produce a 100-word summary for the whole cluster. We are also trying to avoid sentence redundancy, which turned out not to be a problem in single document summarization, but it may be a problem in multi-doc summarization, where we can have even identical sentences appearing in two different documents. So we just set its empirical threshold on sentence similarity. So if the similarity between two sentences exceeds a certain threshold, then we'll only consider one of them to be added in the graph. And then for the evaluation, we built the summaries for the 59 clusters, again from the Document Understanding Conference in 2002. And we'll look at the top 5 performing systems and the baseline, which was provided by the organizer and is basically the first sentence in each document. And we look at the best performing algorithm from the single doc summarization. So we have PageRank and HIT. And these were used to build the single doc summaries and then also the meta summarizer using the same algorithms. And these are the results. And also for comparison, see the results from the top 5 systems.
Have you looked at error bars in those numbers? They seem very close.
Yes, they are very close. I mean, compared to the baseline, it's significantly better. If you were to compare these with what other systems have done, or also in between. I mean, if you look at PageRank compared to HIT, it's not a significant difference. Still, what I find very interesting and would be particularly useful if you want to move this to another language or another domain is that it's completely unsupervised. So although, like in this case, it's not even better than the best system, the fact that it's unsupervised, I would say that it makes it particularly appealing when you want to move to other data or other languages. So an intermediate conclusion using... Yes, sorry.
I just wanted to ask quickly, did you actually ever try to evaluate Rouge at every iteration of your algorithm to see whether going to convergence is really what you want, or you want to stop at an intermediate level?
No, I think it relates to...
All right.
No, I didn't.
I didn't paraphrase his question with mine.
It was a good summary of my question.
Carry on.
He said Rouge, I don't think
Yeah. It's a better summary.
But you said the two had a similarity to
It was interesting to look at that. I mean, I didn't. I just let it converge and then look at the final result. But it would be interesting to see what's happening. Although it would be nice to see that you get better results in between, but then you run into other problems, like where to stop it.
Yeah. You probably don't get better results in between, but you should stop early. And if you can stop after 3 iterations, that would make recovery much faster, and then 20 or 40.
Right. I mean, if you can determine that the third iteration is the best, but if, say, for some text would be the third iteration and for some other text would be the 10th iteration, then how do you do the iteration? So, but it will be nevertheless interesting, and I'll consider looking at that, see if you can get better results before this convergence. So this algorithm, as I said, is unsupervised, which makes it particularly useful for application to other languages or other domains. It gives a ranking over all sentences in the text, so eventually it could be adapted to longer or shorter summaries, and does not require any training data. So what I would like to show for the rest of the talk is outline a couple of other applications that we tried within this same framework of graph-based ranking algorithms. One is worsened ambiguation, which is an unsupervised solution for that using machine-readable dictionaries. And the other one is keyphrase extraction. And there are some others that we are currently looking at, like domain classification. Also, we are trying to do something on word alignment. If things are going to work out, maybe you'll hear more about this in the not too far future. So for worsened ambiguation, considering a text, I would take all open class words and try to get all the meanings as provided by a given sense inventory. So we work with WordNet. So in these experiments, WordNet was the machine readable dictionary that we used. And then you try to identify some semantic relation, again, as provided by the dictionary. And here you end up with a graph. So we have the various senses and the various semantic relations. And once we have a graph, we can apply the graph-based ranking algorithm and try to find those vertices that are more important. Now, if once we get the importance of the vertices in the graph, we can look for each word what would be the most important vertex. So, for instance, for soldiers, you would look at the vertices, at the score of all the vertices that are connected to this word, all the senses, and the one that has the highest score eventually would be the correct sense. So the way it works, first we start by assuming any possible meaning as a potentially correct one. So all the meanings would be inserted in a graph. If we were to talk in WordNet terminology, basically all the scene sets will make a vertex in the graph. Then we draw connections between vertices. We are using WordNet relations like hypernymy, synonymy, entailment, and so forth, all the relations that we can draw from WordNet. And then apply the graph-based ranking algorithm and end up with some scores attached to the vertices, to the scene sets, which can be used to select the more appropriate word senses. And this really relates to the lexical chain solution that was proposed time ago also for finding word meanings. So the lexical chains were computed rather statically, whereas here we have also this iterative factor. So we evaluated on the sensible to all words and the subset from SEMCORE, SEMCORE being the corpus annotated with WordNet senses, and also compare with two related algorithms. What would be the LESC algorithm, which tries to identify, again, using exclusively information from a machine-readable dictionary, would identify those senses that have highest overlap, the highest overlap between their definitions. And this is the way to decide on the correct sense. And then baseline, which would be, depending on the experimental setting, we'll look at most frequent sense as provided by WordNet or a random sense. So the two different experimental settings, one was we call it uninformed, where we do not take into account the sense order rendered by WordNet. And so the baseline here is the random baseline, just pick a sense at random for each word. Then we evaluated LESC, and that gave about an improvement, so it gives about 43%. TextRank, which is this algorithm that we are actually using PageRank here, so we didn't look at it, hits and positional power. So this would give 47%. And then there is a combination between TextRank and LESC, which provides the best result for this setting. Basically, what this means is that when TextRank cannot make a decision on a sense, rather than backing off to the random sense, it will back off to LESC. So that's the way we combine the two. And then we also look at an informed setting where we take into account the sense order from WordNet. So the main difference here is when, again, one algorithm cannot make a decision about the word sense, it will back off to the most frequent sense in WordNet rather than doing that to the random sense.
Since the graph is only linking words that are present in your text, what is the unit of text that you use? Is it just the entire text?
Yes, yes. And that will...
Are these broken up into like semantically coherent documents, or you just took the entire body?
No, we took the entire body. And the kind of text that we have in this test bed, they are usually coherent. So they all talk, the entire text will talk about the same.
So the question I had actually is that your graph is going to be highly disconnected, right? Because you only get a connection when you have two words that are in fact adjacent in the WordNet hierarchy, either that are related in the WordNet hierarchy in some way. So you're going to have lots of words that are that have no relationship to anything. Did you look at how many words are completely unconnected, or how many disconnected segments you have in the graph?
If you look at an average text about 800 words, open class words, you get about 80% average. But again, because we look,
all the words?
Yes, so about 20% are remain disconnected. And it's also because, and that turned out to be the kind of relation that worked best, we really take everything from WordNet. So if there is a domain relation, which is pretty strong, which came out with WordNet 2.0, if there is a nominalization relation, any kind of relation that you can draw between two concepts will be added as an edge in the graph. So that makes it more connected. If you want to constrain and say, I'm only looking at this relation, probably you'll end up with that problem that you mentioned.
When you say 80%, so 80% of the nodes had some relationship.
Yes, yes.
But were they, I mean, how many disconnected segments in the graph did you end up with?
We didn't
I mean, you
really
can have
look
two words
close
that are
at that.
connected to each
Yeah,
other.
they are, but you still have, I mean, in most algorithms, in PageRank, which is the one we use here, you still have that factor that allows you to do a random jump. So you can go from one subgraph to another subgraph because of that. So the random jump in the algorithm would allow you to go to travel between disconnected elements. So you still get them connected in that way. So it's basically like PageRank would they say to implement this random surfer model, but probably you are familiar with that. It's a user that browses the internet and will click with a certain probability on links that are outgoing links from a certain page, and with a random and with a smaller probability, usually 15% in this PageRank model, would jump to a random page. And that's the same that happens in this graph that you get with concepts. So with a high probability, you will move from one concept to another semantically related concept. But then with somehow smaller probability, you would just jump to a new concept. So that would make you the move for the another subgraph in the text. And that's where I believe, I mean, something like MindNet, for instance, could help, where you have a much richer set of relations. So it's not limited to what lexicographers thought of, like it's the case with WordNet, where they thought of these relations and they put them in there. It's not something like MindNet would have something that was learned from text.
And these edges are unweighted in this
Yes,
application?
yes. In this, yes, it's unweighted and it's undirected. So, okay, to conclude here, this would be, again, for the informed setting, where we look at the sense order in WordNet. Again, TextRank provides better results than less. A combination did not help much, probably because of this bias toward the most frequent sense. So when you combine the two, you don't really gain a lot. And finally, the last application that we'll look at and experimented with is keyword extraction. Now, in this case, we have open class words from the text, and the edges that connect these words are co-occurrence relations. So if two words co-occur within a certain window, and we look at the window between 2 and 9 words, then you draw an edge between those, the corresponding vertices. And basically, in this way, you end up with a ranking over the words in a text, and those that get higher in the ranking would be those that are eventually more important for the text, so it would be the key phrases. And we, before adding words to the graph, we run this through some syntactic filters. So we look at adding only open class words, adding only nouns and adjectives, so various combinations. And the evaluation was done on what seems to be a standard data set for key phrase extraction, was previously used in key phrase extraction experiments. We are only looking at the test data because, again, it's an unsupervised approach, so we only look at the a test data set of 500 inspect abstracts. So these are a collection of abstracts from computer science and information sciences. And previous work mostly used supervised approaches. There is work by Peter Turney, who was using genetic algorithms. More recently, rule induction done by Annette Hull. And this seems to be the state of the art in this area. So she was measuring precision and recall on this data set using 1,000 abstracts for training, 500 for development, and 500 for test. And these are the results. So I'm showing the first 3 rows are from Annette's system, various combination of features that she used for her system. And the last row is what TextRank is doing. So basically what we do in this setting, we looked only at nouns and adjectives, and then select the top third of the words. Since these are abstracts, you really end up with a fairly small graph.
What are the links in the
Co-occurrence? Co-occurrence. So if they co-occur within a certain window, then you would add a link between the two.
And you use the co-occurrence counts as weights, or is that?
Yes, yes.
So it's not going to be heavily weighted towards the more frequent words?
It will, but it will also, I mean, if a frequent word co-occurs with another word, then that word will also get pulled out just because it happens to co-occur with this word that is more important. So if you look, and we look, I don't really have an example here to show, but we'll look at the rankings that you get if you do simple frequency count or if you do it with these algorithms, and they tend to be completely different.
So you're expecting only keywords, not key phrases?
It's also key phrases because we look at the adjacent words. So if two words, so in the graph you actually have words, so single words. But then if two or more of these words that are found to be important by this algorithm happen to be adjacent to each other, they will form a key phrase. And so again, the F measure that we obtain is higher than results obtained with the previous approaches. We are doing better in terms of precision, although the recall is still higher, apparently, with the supervised method that Annette was having. So she is getting a 51% recall on this data set, but we are getting significantly higher precision. And overall, the F measure seems to be somehow better. And again, this is unsupervised. We did not use any training data. So eventually, now, in this particular experiment, we are using part-of-speech tagging. So you could move it to another language if you have a part-of-speech tagger for that language. So to conclude, I presented a framework called TextRank, which applies graph-based ranking algorithms to text processing. And it relies on graph representation of text, which model in a natural way text cohesion, and relies on global, this kind of algorithms rely on global information that is recursively drawn from the entire text. And so far we experimented with the application of this framework to several NLP tasks, extractive summarization, resolution of semantic ambiguity, and keyphrase extraction. And they seem to be competitive with state-of-the-art for these particular applications. And really, to conclude, to go back to the original analogy, all sentences, concepts, keywords are equal, but it turns out that some are more equal than others. Thank you.
I think we still have a few minutes for questions.
Going back to the word sense disambiguation application, have you done any error analysis?
That's something that we are currently working on. It was also pointed out by other people that would be interesting. I don't know if you refer to these, but one suggestion was that if we could see whether, if we only look at hypernymy relations versus looking at meronymy only. So depending on the kind of semantic of the kind of relation that you have, whether you get better or worse results. So really look at the data, look at the output that we have, and try to do an error analysis and where those errors come from, and also try to estimate, and that's something that we want to look at, try to estimate that if we would have a richer semantic network, then if that's going to help.
Because, I mean, some things that, because you're not constraining the links at all, given your syntactic information, as you were showing earlier with the semantic parsing.
Mm-hmm.
So in this context, you know, soldiers, people, blah, blah,
Yeah,
blah. Then you say, you know, they were weakened because they had a lack of vegetables. Well, if you just let that go, vegetable is going to come out as a person, so it'll count as an error. Because the vegetable will be, you know, the human sense of vegetable will come out much more highly scoring.
Yeah, I agree.
So
I
that's
agree.
the type of error that I would expect to see, that the chaining is not it, because you have syntactic evidence that it cannot be that sense. So, you know, you have the information in different projects, so you should maybe look at applying that.
Yes, that's all future work. So we want to do also and look also at constraint ranking. So when you build a graph, rather than allowing the flow to go between any two vertices, just constrain it, like pretty much like people working on spreading activation would do. So you can have constrained activation. So only if this link is of a certain type, you would allow the flow to go to the next vertex or not. So, but then again, all this is, I think there are a lot of improvement that could be done. And I agree. And it's also the fact, for instance, you have that 1 sense per discourse, which at least for the WordNet sense inventory was proven by Bob Kroves to be pretty weak. And we are doing that. So since we look at the entire text, we rely on this 1 sense per discourse, which may not turn to be true in some cases. So there are all sorts of ways to improve it.
So for keyword extraction, you said you use a part of speech tag, and in some sense I'm sort of getting up here to see one application of part of speech tagging, right? So, but my question is, why didn't you try there, or maybe you tried to use TF-IDF, take the whole body of documents and just put some thresholds also, as you did for sentence extraction, and don't care about part of speech at all, see how that does.
I did try, and it was worse, and I believe one reason is because so far in all these applications, we only look at the text itself, so without any outside information. So eventually, if I would take the TF-IDF out of a large corpus, then I would get something meaningful. If you only count some frequencies in the text, so we didn't want to move outside the text, just try to keep them down to that particular text and as unsupervised as possible. But it would be something. So we only did some frequency counts, and rather than using nouns and adjectives, we'll do like those that are more frequent, we'll make it in the graph and then apply the graph-based ranking algorithm. So it's not really a TF-IDF, but something that would simulate that. But that would be something to try, and that's what we try to do also for the sentence extraction, to move outside the text and try to get some counts from raw corpora, so that just get some TF-IDFs or some other counts that would give you an idea of the importance of a word in general in language, not for that particular text.
Do you have some sort of like intuition as to when you expect like these graph algorithms to do better than, you know, a simpler thing that just looks at the in degree or whatever? Like in what domains or what applications you think that, you know, this is more likely to work? So that if we have some particular problem that we're trying to solve, like, you know, how do we know, should we try to apply this, or should we, you know, not? Do you have kind of an intuition as to when that might be good?
I think where you have a lot of connections between entities. So when you have, like, for instance, in a sentence, in the sentence extraction application, it's not linear connection. It's really you end up with a graph. And there is this kind of work is also applied for discourse processing. There are people at MIT that actually apply kind of graph-based ranking algorithm. So where you have a lot of connections between entities, rather than having some linear structure, a lot of connections. I believe in those kind of applications this would help. But then I'm not sure if that answers your question, because even in that case, I mean, the degree of a vertex would really apply when you have a graph structure. So it is something that we need to look at and see where is that you get more from doing this in a global way rather than just looking at the local information, like the degree of a vertex. In what we've tried so far, it seems that global information helps more than local information. So probably that would be an answer, where you need global information drawn from the entire text to understand the particular unit, then maybe this would help. Where simply local information is enough, probably you can just look like the degree of the vertex, and that will give you the information you need. But it's just an intuition, it's very speculative.
Yeah, that's all I was asking.
How do you filter out some words like articles or other
Can you
words?
say louder, please?
How do you filter out some words that happen very often but do not hold any meaning, like articles or anything else, like a, the, on, of, or just the words that happen in every sentence but do not have any meaning, do not affect the semantics of the text?
Well, those would eventually get filtered out because you only look at open class words. So if you do some tagging before, then you would only look at nouns and verbs, and so those kind of words will get filtered out. There may be, again, some other words which are open class words which are not very meaningful. And at this point, we don't attempt to filter them out for any of the applications. When we say we apply a syntactic filter and pick all the nouns, we really pick all the nouns, regardless of how meaningful they are. Or is this what you're asking?
Since we've still got time, and since you're at the beginning of your presentation touched on other interests of yours, I'd ask about your interest in using the web as a data collection mechanism. Can you say a few words more about the kinds of data you're collecting and what kinds of issues you encounter as you collect that data?
So far we collected sense annotated data, and that is the data that I mentioned that was used for sense eval. There is a related project that the team is actually doing, my collaborator Tim Shlovsky, on collecting common sense data. And the main issue, I think, regardless of the kind of data that you try to collect, is once to make sure that the data is clean. So for some annotation processes, like for word senses, we collect at least 2 tags for each example. So we are seeking agreement just to make sure that the annotation is correct. And then another big issue, turned out to be a big issue, is really motivating users. So having them come back and having them really contribute data. If one really takes care of this, like it was the case right before sense eval, and I was desperate that I didn't have enough data. So I was really taking care of this and every day sending out gift certificates and other things. And it worked out, and there were a lot of contributions. If you just let it there, it still works out, and there are quite a few contributions. But again, this seems to be an important issue that needs to be taken care of to really motivate the users. And one thing that we are trying to do, but it doesn't really work for all kinds of annotation processes, is try to give immediate feedback. That seems to make users happy. Like for instance, if you have word senses and they annotate an example with a sense, and you tell them, yes, this is correct, or no, it's incorrect, then it will motivate them more. But in some cases, it defeats the purpose. So we really want to collect annotations for new text, so we don't really know the sense for that text.
When you have multiple annotators, do you hide the annotations from previous annotators, or do you reveal them after they have done they've made their contribution, so they can see how they compare with others?
So far, we didn't reveal any of those. So they're just kept internally. And also, we wouldn't show those not to bias other annotators. So, but that would be, I mean, something that we've been thinking of. We didn't really get too far, at least not up to this point. Try to have a scheme where if you have, say, annotations already collecting from 2 users, then you could use that to give feedback to a 3rd user and say, yes, you did okay with this annotation or not. So try to give feedback based on data that you collected, again, from web users.
Give them a kappa score or something.
Yeah, something.
Use the graph-based method itself to give, so that some people become authorities. If lots of people agree with them, they become the authority.
Yeah, that's something really, like last week I was talking with one collaborator, and he was suggesting this as for trust analysis. So you have trust networks, and you can really use the graph-based ranking algorithm to decide which are the entities to be trusted in the network, and then build on top of that.
Do you have experience with abuse? If people come in and try to label your data with garbage?
It happened only once, and it was apparently a kid. And then his elder brother wrote to us and said, look, my little brother annotated 500 instances of yours. His login, please remove his data because it's used. Otherwise, I mean, it seems that people tend to take this pretty seriously. I mean, those who end up really contributing data, they take it seriously. And also, I mean, we put all those slogans and saying that this is used for science, and so they tend to take this pretty seriously, and they wouldn't really make malicious contributions. So. And you can also kind of spot it, like in this particular case, we also knew because somebody told us, look, this contributor is just put some data in there. And you can see because we have all these records of the annotation process, and if you see that somebody is annotating 500 instances in 10 minutes, then something is wrong there. So can just rule that out and put it back to the pool of data.
How many contributors have you had?
It's in the order of hundreds, so it's some hundreds. For the English task, for instance, for Romanian it was less, and of course we are targeting a much smaller community. And then when we also have data for English Hindi, it was really very hard to attract users because it's imposing a constraint. So the users have to be bilingual, so be comfortable both with English and Hindi, and so that was even harder. But for English only, it was. I mean, we are happy with how many users we have. And then one thing is also something that we are thinking of. I don't know if it's going to work out or not. Is to try to really put this into games. So something that is really attractive and motivating for people. Like, we also try to make this as a game and call it a word game, but at some point it may be boring. So
And how do you recruit annotators?
well, in my classes, yes, and
So mostly from the university community.
yeah, I mean it's not mostly, like about 20% would come from, because we also have this feature that you can use this as a class project, so a professor could have a login and really monitor what the students are annotating, and it was used in several classes. It was used in the States, in England, in several universities. They use this because you really can show students, like, this is how people would annotate data, for instance, with word senses. So really showing them this all lexicography aspects and how you pick between several senses. So it made an assignment for several NLP classes. And that's about 20% of the contributions come from using platforms.
Do you present multiple choices, or are you presenting open word box, text boxes where they can provide arbitrary input?
It is multiple choice.
Always.
Because you're trying to map to word that sense.
If there is internet here, I don't know if there is. Probably not, no, because I didn't connect mine. It's online, so if you feel like contributing some, it's there.
What is the URL?
It's Teach Computers, teach-computers.org, and that will take you to all the activities that we have in.
I know, I looked at it briefly through Ada's website also.
Yeah, and I have it on my website. I'm advertising.
What about the common sense knowledge, though? I mean, it doesn't seem to me that's open-minded. Okay, so that's open-minded, but how do you annotate? You don't have multiple choice options there, do you?
No, it's really not my project, so it's just telling you about it. They collect common sense assertions, so people would just say things that are common sense. And then internally they try to group that somehow. I don't know, like these are kind of assertions or... And very, very recently, like 2 days ago, I noticed an email by Parsing, who's the leader of this Open Mind Common Sense project. And there was an email announcing ConceptNet, which is apparently a semantic network that was built on this Open Mind Common Sense data, but I didn't get a chance to try it out. So it's something really recent. So apparently they did come out with a resource out of this common sense data. And then what Tim was trying to do is to try to guide this collection process. So rather than just telling user, tell me something, like a common sense statement, he would ask questions. So he would try to guide this process in a more meaningful way. So he would get the information that a computer wouldn't know. So if there is already an assertion saying about what an animal would do, then he wouldn't ask the same thing about dogs or cats, because he already knows the general concept, animal does this or that. And so he would try to guide that through some smart way of asking questions to users. And it's going to be pretty big. I believe it's some hundreds of thousands of statements. But at least in size, it does compete with OpenScience. But then in terms of uses, I don't know. I mean, not even OpenScience, but I don't know how often it's used.
Find the speaker again.